to the fourth lecture on earthquake resistant design of structures. In this lecture, we would be discussing more about static codal methods for design of structures to earthquakes and also solving a numerical problem. Let us take a summary of what we have studied till now in the previous lectures. First of all, what is earthquake? We discussed that in the first lecture. What are the major earthquakes of history? What is acceleration time history? What is response spectrum? What is DVA response spectrum? In the second lecture, we discuss how do we develop response spectra. In the third lecture, we discuss about what is design spectra, the design spectra in different codes, and what are the different methods of earthquake resistant design. So basically in the last 120 years, if we have a look at the map of the Middle East, South Asia and Central Asia, a number of 7 magnitude and higher earthquakes have occurred, but most of these can be seen along a fault line which are predominantly known. Now this is important as it helps us in building of a hazard map. The location of the cities and the major population centers on this map can give us the risk assessment. The data related to the lithosphere of the region is also beneficial for studying the risk assessment of the area. Based on the intensity of the earthquake, seismic hazard map is developed for the world. The intensity takes into account the effect of earthquake and the likely damage or the risk assessment. It surely depends on number 1 on magnitude and number 2 on the population to be affected. The red zones or the dark red zones that are shown in the map are the highest risk zones of the world. Next is the seismic zonal map of Iran and other neighboring countries, which shows the likely or the probable seismic hazard, the peak ground acceleration, which varies from 0.05 to greater than 0.32. Most of the locations in Turkey and Iran can be seen to have high peak ground acceleration. This area of the world is one of the most seismically active ones. So from the seismic hazard map of India, seismic zones of India have been plotted and they are given in IS 1893. The regions that are divided into 4 zones, zone 2 to zone 5. Zone 1, which is given here in blue, is existed earlier, has been scaled up to zone 2 now, and so there is no zone 1 any longer. So the regions that you see in blue are now zone 2. As discussed earlier, zone 2 has low seismic intensity and the Z value of 0.1, while as zone 5 has got seismic intensity to be very severe, and this is in orange or pinkish color with the Z factor to be 0.36. The regions of India that are in zone 5, the most highest risks are the northeast, the Srinagar region in J&K, certain regions in Himachal Pradesh, and the Kutch region in Gujarat, besides a portion of near Sikkim. Now, what is the Z factor for different cities in India and in which zones are they placed? Let's take an example given from IS 1893, wherein there are 4 zones, zone 2 to zone 5. The city Pune, for example, comes in zone 3 with a Z factor of 0.16. Similarly, the city Delhi comes in zone 4 with the Z factor of 0.24, and city Imphal in Srinagar they come in zone 5 with the Z factor of 0.36. Now, depending on these zones in which the T's are placed, one can now come to the determination of the design seismic base shear. Now, we know from the earlier lecture that the design seismic base shear for a multiple story building could be determined from VB is equal to AH into W. W here is the seismic weight, and that will be defined later on. AH is the seismic coefficient that we have defined in the earlier lecture, wherein AH was equal to Z by 2 into I by R into SA by G. Now, SA by G, the spectral acceleration, was already defined in the earlier lecture. I by R, I factor and R factors were also defined. The Z factor was described here above for different zones and for different stages in which the structures are to be built. Thereby, we could get the value of the base shear VB. For the determination of SA by G, what we require, if we recall from the earlier lecture, is the value of the time period of the structure. Now, the time period of the structure could be determined either from knowing the value of K and M and using the formula for omega is equal to under root of K by M. But if we are unsure about the values of K and M for the structure, there is a method to estimate the time period of the structure, although these are approximate methods, but they are quite simple. The first method for the reinforced concrete frame buildings without infills, it gives us that the time period is 0.075 into h raised power 0.75. Now, h here is the height of the building. Now, for RC frame buildings and other buildings which are not RC frame buildings and RC frame buildings with infills, the time period could be estimated from TA is equal to 0.09 by under root of D. Now, D here is the dimension of the base. It's the dimension of the base of the building along which the time period is being determined. So, once we know the time period of the building, we could determine the value of SA by G, and as we saw earlier, thereafter we could determine AH, the seismic coefficient, and finally the base shear VB. Now, if we know the value of VB, we could go for determination of the design lateral force that is acting at each floor I, at any floor I, that could be determined as QI is equal to VB into WI HI square by summation of J varying from 1 to n WJ HJ square. Now, this is from IS 1893. Thereby, from this formula, one could determine the lateral forces at any story level or the floor level if the base shear is known and if the seismic weights of each of the stories is known. Now, we would be solving a question in order to determine the earthquake forces or the lateral forces by static method of analysis. The first thing that we need to do is to define the question. The question given to us here is that there is a plan RC frame building with a plan area of 3 into 5000 mm in this direction. So the total length in this direction is 15 meter, and in this direction 2 into 4000 mm each. So we have the plan length in this direction to be 8 meters. Now this is the x direction and this is the y direction. Now the elevation is given to us. There are 4 stories, and at each story W1, W2, W3 and W4 are the seismic weights. The 4 stories each has a height of 3150 mm. So the 4 stories have a height of 4 into 3150. Given that this is the question given to us, certain other things are also provided to us. The area where the structure is located is Delhi. It comes in zone 4 if we take the seismic map. The soil conditions where the structure is being built or the building is being built is medium stiff. The RC building is with infill walls. The dead load which slumped at the floors from the columns, that comes to be around 15 kilonewton per meter square, and the live load is 4 kilonewton per meter square. These are the things that are known to us. Next, the first thing what we need to do, we need to determine the seismic weights. Seismic weight W. What is the floor area? Its length 15 meter into width 8 meter. That comes to be product of B3 into C3 here, that is 120. Now there is a clause given in IS 1893 part 1 7.3.1. you can have a look at that clause, wherein it states that whenever you take the live load, you take it only 50% for the structure. Now when we are calculating the live load, let us first of all determine the seismic weight W1. W1, as we know, is for the first floor, and the seismic weight for the first floor would be the dead load first. It would be 15, it's given to us 15 kilonewton per meter square into area. That would give us, area is 120 meter square. The total dead load would be B7 into C7, that is equal to 15 into 120. Next, we are determining the live load, but the live load has to be taken to be only 50% for determination of seismic weight for all stories except the top roof story. Now it's would be 2 because the live load is 4 kilonewton per meter square. 50% of that is 2. The area is 120 from here, and the total live load would be 250 B9 into C9. So the total load would be 1800 plus 240, that's 2040. Now W2 would be same, 2040 for the second story. For the third story it would be again same, 2040. But for the fourth story we have to only take the dead load. No live load is to be taken for the top story, the roof story. Thereby, what is the dead load? It's 1800 from here. So for the fourth story, W4 is 1800. So we can now put this into the figure. W1 is 2040, W2 is 2040 kilonewton, W3 is 2040 kilonewton, and W4 is 1800 kilonewtons. Now let's move to determination of the time period of the structure. First, in the x direction. The x direction is this direction. In this direction, how do we determine time period TA? As I told you earlier, TA is to be taken as 0.09 into under root of divided by under root of D for RC framed structures and other buildings with infills. Now D here in x direction is 15 meters. Thereby TA would be 0.09 divided by under root of 15, so it would be 0.04 seconds. Now we know this SA by G from the earlier lecture. The type of the soil that we have here is medium stiff. Thereby, for medium stiff soils, when the time period is between 0 to 0.1, the formula that we have to take is 1 plus 15T. That would be, we have T between 0 and 0.1, it's 0.04. Therefore, SA by G would be 1 plus 15 into T. T here is B7, that's 0.04. So SA by G we get that as 1.603 or 604. From there, we can now obtain the value of AH. What is the value Z for Delhi? For zone 4, it's 0.24. What's the value of I? For a simple type of building, it would be 1. What's the value of R? For RC building, a normal RC building, it's 3. Thereby, Z by AH is Z by 2 into I by R into SA by G. SA by G is 1.603. Thereby, AH would be 0.064. So, VB is equal to AH into W. Now, W is known to us for all the stories. What is it? If we calculate the total W for all the stories, it comes to be 7920. Thereby, VB is 0.064 into 7920, which is 507 kilonewton. Thereby, now we have the base shear in X direction. Next, first of all, to calculate the time period in Y direction, again using the same formula, TA is 0.09 by under root D for RC framed and other building with infills. Now here D would be 8 meters in Y direction. Thereby, time period TA would be 0.031 after calculating from here. Again using the same formula, because TA is again between 0 and 0.1 for the medium soil type, which it is, the structure is being constructed in. SA by G would be 1 plus 15 into B7. So we get the value of SA by G equal to 1.477. Thereby AH, which is the seismic coefficient, would be equal to what we did earlier. Thereby we obtain the value of AH equal to 0.059, and VB, which is the base shear, is AH into W. So VB we obtained as 0.059, which is AH, into 7920, which is the seismic weight. So we got the value of VB equal to 467.9 kilonewton. Now we have the base shear in both the directions. It's 507 in X direction and 467.9 in Y direction. Now next we do the lateral load distribution. So we build up a table like this. In this table, first of all we develop the story levels from top to bottom, 4, 3, 2, 1. We then write down the seismic weight of each story. What's the seismic weight of the fourth story? The roof story? It's 1800, it's 2040, 2040, 2040. So we have 1800, 2040, 2040 and 2040. Now what is the height from the base till the floor level of the story? It's 12.6 meter. If we measure from base till top, it will be 12.6 meter. For third story, from base till third story level, it's 9.45. Likewise for second story it's 6.3. For first story it's 3.15. Now I can determine the value of Wi into Hi square. Why do I need to determine this? Because I have to determine the formula for lateral force distribution is this: Qi is equal to Vb into Wi Hi square by summation of j varying from 1 to n Wj Hj square. So first I determine Wi Hi square. So after determining from here Wi into Hi square, I get this value. Similarly for this story I get this value, for this story I get this value, and for this story I get this value. Now I also need to determine the summation of Wj Hj square. So I sum all of these from D6 to D12 from here up till here, and I get the value of 569154.6. Now the ratio of Wi Hi square by this summation, what do I get? For the first condition, it will be 285768 divided by this value, the summation value. So this is the value, D6 divided by 569154.6. So I get the values similarly for the third story level, 182177.1 divided by this. For third story, 80967.6 divided by this. And fourth story, 20241.9 divided by this. Thereafter, now I'll be in a position to determine the value of Qi, which is the lateral force distribution at each story level. In the x direction, I have the value of, what's the value of Vb that I have? It's 507. So I multiply Wi Hi square that I obtained from here, this ratio. I multiply it by Vb by 507 in x direction. So I get these values. Once I multiply this by 507, I have done that. 507 into F6. I have obtained all these values. Similarly, in y direction, what's the value of Vb? 467.9. So I multiplied this value here by 467.9, F6 into 467.9, similarly F8 into 467.9. So I obtained these values. Thereby, I have now obtained the lateral forces, that the design lateral forces that are now acting in x direction and y direction at each story level. Thereby, now I can define in the x direction what are the forces. Let's recall. The forces are 254.56, 162.28. It's 254.56, 162.28. Then similarly 72.12 and 18.03. In y direction, it's 234.93, 149.77. So what I obtained here is 234.93, then 149.77, 66.563, and 16.641. So this is the lateral distribution of forces for the structure in x and y direction. So we have now statistically analyzed the structure in the static mode for earthquakes.